The patterns we've seen so far are all from the original Gang of Four book. In particular, we've seen three categories of creational, structural and behavioural patterns that were originally proposed by the Gang of Four. I'd now like to move on to talk about some somewhat more controversial patterns which are claimed by many people to be modern design patterns. All of the patterns' acceptance in the community is dependent on who likes them, who believes in them, who promotes them. So even some of the Gang of Four patterns today are being argued that they should be either revised or retired because programming styles have changed. When we get to modern patterns, this can be even more controversial because people are actively debating what's a good pattern, what should be accepted into the canon today. So, the ones I've chosen are reasonably uncontroversial. They are probably influenced by my own subjective experiences, by the kinds of work that I do, the kinds of jobs that I have had. In particular, I used to work as a hedge fund trader. I was working very heavily with financial data, and so the patterns that I personally know and like and that I choose to present here are likely to be quite influenced by that world. I also work today in robotics, which brings me to the first of these modern patterns, the publish-subscribe pattern. Now this is very close to my heart because this is the foundation of everything we do in robotics research today. We, in robotics, use a middleware system called ROS. That stands for the Robot Operating System. It's not, in fact, an operating system. It is a piece of middleware that runs on top of a regular operating system. And it is basically just a big instantiation of this publish-subscribe pattern. The publish-subscribe pattern can be viewed as an extension of the observer pattern, which we saw earlier. Remember, in the observer pattern, we have one subject, we have a bunch of observers, and the observers register their interest with the subject, so that every time the subject changes something that the observers are interested in, it calls them back using callback functions to inform them of the change. That means that the observers don't have to sit around constantly polling the subject to ask whether something has changed or not. The publish-subscribe pattern is a generalization of this. In publish-subscribe, we can have a whole bunch of objects who can all act as either or both of subscribers or publishers. That means that every object in the system can be notified of changes coming from every other object. This is done using a system of topics and messages. The publish-subscribe pattern is heavily influenced by human message passing systems such as newsgroups, or today social networks. In a newsgroup, you have a bunch of topics. Everyone in the newsgroup community can choose which of those topics they're interested in, which they will subscribe to. So for example, you might be interested in guitar playing, so you subscribe to the guitar playing topic. You might also be interested in the design patterns topic for discussion of software engineering, so you subscribe to that. But you're not interested in the thousands of other topics out there, so you don't subscribe to them. Anyone can then publish messages to these topics. So if I have something new that I'd like to say about guitar playing or design patterns, then I will post my message to that topic. And at that point, everyone who is a subscriber to that topic will be notified that a new message has been posted there. The implementation of this is done similar to the observer pattern using callback functions. So when I choose to publish something to a topic, that's my choice to do that. That's part of my thread of program execution. But at that point, the topic itself will be acting similar to a subject in the observer pattern. The topic will maintain a list of who are its subscribers, and at that point it will notify them all that the new message has been published. So this pattern is the foundation of everything we do in robotics. In the ROS system, there are thousands of people all writing pieces of code called nodes. Those nodes communicate with one another via the publish-subscribe pattern. All the nodes will publish messages to topics. Those messages aren't human readable strings like in a newsgroup, but they have standardized formats which everyone knows and which everyone can understand. So for example, if you're writing a device driver for robotics, like a laser scanner driver, you'll create a laser scanner node. You will publish a standard format message to a topic called laser scans, and then all the other programs which are interested in that LiDAR data will pick that up. So you might have multiple programs all subscribing to that topic, which are each doing things like feature extraction and object recognition. Now, this is interesting because it creates a different type of API to other forms of software engineering. Usually, when you want to use other people's code, the API consists of a list of function headers. We usually use function headers to communicate both between software and between the humans writing that software to describe what each part of the software is doing. So this is a different way of creating a technical and human API. In robotics, we don't usually call other people's functions at all. We instead get an API specification for what their node is doing, which comes in the form of a list of the topics and the message types that will be posted to those topics. Everyone in the robotics community learns to speak those standard topics and standard messages. So for example, a command to move a vehicle around, we have a specific style of message called a twist message, which everybody speaks. Every robot can accept that command. Every AI controller can publish that command. This tends to create a different kind of interaction between software and people. It's a looser form of interaction than having to study each other's function header APIs. Often when you communicate with messages, you move more of the logic inside the nodes. It encourages more hiding state and of algorithms, and it encourages these very small, simple, and very standard interfaces that are all compatible with one another, which is why we like it in robotics. The next pattern I'll talk about is the Model View Controller, usually known as MVC pattern. You have all used software based around this pattern, such as LibreOffice Writer or other word processing, desktop publishing packages. Also the document object model on web pages. What you see in a program like a word processor is there is some actual data called the model. So the model describes the underlying document being edited here. That is distinct from what is shown to the user on the screen or otherwise. Usually in an editor like this, you will only be looking at a small part of that document at a time. You can't see the whole document. You can't see the whole model, even though it's there. Even the stuff you can see could have invisible components. For example, a paragraph of text, as shown here, could also contain information that isn't immediately rendered. For example, it could have information about how to display foreign language characters, which aren't actually present in the text, but the information about them and how to display them is still carried there. So here we split the model, the actual data, the document itself, from the view, which is this graphical user interface, GUI, or any other kind of partial display. The view also provides an interface for the user to tell the system what to do, such as icons to be clicked on. The third part of the system is the controller, and the controller is a non-graphical component which provides a user application programmer interface, or API. So the difference between an API and a GUI is that an API consists of usually a bunch of functions, programmatic functions that anyone can call, whereas a GUI is a graphical interface consisting of things like icons that can be clicked on. So in MVC, the controller is a strictly non-graphical component. It sits there as a programmatic interface and it exposes all the things that the software can do. For example, there could be commands to insert new characters into the text. There could be commands to delete text, to reformat text. They're all the things that you find in an editor like Vi. If you program Vi, the difference between the view and the controller is very clear because Vi users are used to mapping commands from the controller to key presses inside the view. Every time you write a Vi map command, you're linking a view activity, such as pressing DD to delete a line, to a controller command, such as the Vi command delete line, which is part of Vi's real interface. So some of these commands in the controller are to do with updating the model, and other commands are to do with updating the view. For example, there are commands in Vi to scroll the screen up and down to look at different parts of the document. Or in other editors like LibreOffice Writer, there are commands to zoom in and out or otherwise move around the document. If your view includes a GUI, you will typically do a similar kind of mapping as found in Vi, but between graphical components and commands. So when someone clicks on the save file icon, there will be a mapping from that icon, which exists as part of the view, telling it to connect to a command in the controller. So the reason this is useful is because you're clearly keeping the graphical interface away from the controller. In particular, it makes it very easy for other people to come along and call your controller interface programmatically. For example, many spreadsheet users eventually feel the need to get into some kind of automation rather than just typing in and clicking on commands. So if you, for example, run LibreOffice Calc and you want to start programming the spreadsheet itself, you can get in there using a Python module and you can give those commands directly to the controller, circumventing the view. If you're using Microsoft Excel, you can do that with the VBA, Visual Basic for Applications language. Or many Office type applications will have a macro system that let you record the sequence of commands you're giving, maybe from the GUI, and then play them back through the controller that way. Also, if other users come along, they may come up with completely different use cases for your software, which require automation. They don't want to use your GUI at all, and if you use this pattern, you can always provide that clear, sometimes called a headless interface for those people come in and use. For example, we were just running some musical beat tracking software, which originally came with a big fancy Java pointy-clicky GUI, and we decided we didn't want that stuff. We wanted to run it purely in headless mode, and because it was written with this model view controller architecture, it was very easy for us just to give our commands directly to the controller and bypass the GUI stuff altogether. Moving on to the next pattern, the business logic pattern. This is somewhat related to MVC. But this describes a separation of what is called the business logic, which is your model of stuff in the real world. These are objects which have intentionality. They refer to physical objects in the real world. But then you have these other two layers. One is the data access layer. This is where you put all your computational stuff to do with managing data that is used in the business logic layer. For example, your WYSI SQL logic, your super fast database queries to store and retrieve business logic data very quickly. And we have a presentation layer, which is the user interface. That gives your end user an ability to interact with the business logic, which might be a GUI or it might be something else. So this is a very common pattern, especially in financial type applications. I used to work for a hedge fund which was combining automated equity analysis with manual analysis. So they wanted to replace the work of some of the human analysts doing basic accountancy modeling, financial prediction, and present a nice report about the summary of that to some human MBAs who would then make their own decisions based on additional human intuition. So there we had a very clean separation of the business logic pattern. We had a database, we had a whole bunch of systems sitting in the data access layer to make interaction with the database go very quickly. We had the presentation layer where we were creating reports either as PDF files or as interactive GUI displays to show the MBAs what was going on. And then we had the business logic layer, which is the most interesting part of the system. This is where we're actually modeling the real world entities such as companies and profits and money and products. And this is where we're doing our modelling and our calculations. We're trying to predict how different companies will behave, how their accounting patterns will change over time. This is a very common form of system. Database, business logic, presentation layer. Often people who work in these systems will tell everyone that they specialise in the business logic layer. Everyone in finance wants to be seen as the financial modeler. Here's the person who actually understands how to predict the stock market. Often those models are relatively simple compared with what is happening in the other two layers. So when I was doing this, I probably spent about 90% of my time in the data access layer and the presentation layer, just 10% doing the actual modelling, which is what you then tell everyone that you were really involved in. There's an interesting issue here around the meaning of an object in object-oriented programming. The whole category of object-oriented programming is sometimes criticised for not making this distinction. The objects in the business logic layer are different from the objects in the other two layers because they have intentionality. These are objects that model and represent and refer to entities in the real world. For example, if you create a class customer, that does not refer to something inside the computer, it refers to a human being outside the computer in the real world. Or if you create a class car in a transport application, that refers to real cars. This has a different ontological status from the classes and objects in the other two layers. So an object in the data access layer could be something like a database connection or a data frame. In the presentation layer, it could be a PDF document, it could be a part of memory that is used to generate a graphical display of data. But these objects don't refer to anything. They don't have that intentionality connecting them to the real world. Some people would argue that object-oriented languages should make this distinction either at the programming language level or in the software engineering level. For example, you might create a special class called real world object and make sure that everything in your business logic layer is inheriting from real world objects. So you make that distinction more clear. But it's a big criticism of object-oriented programming that it has never really been clear what a basic object is supposed to be. Is it supposed to be a model of something physical, or is it just a computational data structure with some functions and methods attached to it? Next pattern, the snapshot pattern, also used heavily in finance applications. This is an extension of the memento idea we saw earlier. Remember, memento is used to provide an undo function. You're effectively capturing some data that enables you to rewind the system to its state some time ago. In the snapshot pattern, we're not just creating the ability to make one undo, but we're trying to capture the state of the system at a whole bunch of points in time so that we could potentially revert to any of them. So you might see this in an application like a drawing program where you have the ability to undo a whole stack of changes. But you can also consider most finance and accounting applications as instance of this. You need in these systems to represent the state of the world, not just at a particular point in time, but at a whole series of points in time, and to be able to quickly recover them and compute with them. The extreme version of this is stock price data in finance applications, where you care about the very fine temporal history of the prices of things. So software designers often have big problems with this. We tend to invest a lot of time in creating very beautiful design structures that model the state of the world at a particular instant in time. So for example, here is a customer, here is a product, here is an order, here's how all these things relate to one another. And it's very common that we will do that as part of our design process, and then someone, possibly the client, possibly us, will come along and just say, "Oh, could you just make that work with a temporal aspect as well? Could you add some kind of time variable to that so that we can maintain the state of everything over time?" And at this point, your system can go crazy. You might have 100 objects, but now you need 1,000,000 copies of each of those objects to represent temporal snapshots at lots of different points in time. There is a whole issue in metaphysics, in philosophy, about how time should be conceptualized and understood. So in particular, is a customer by itself something that exists right now at the present time? Is a customer something that exists for eternity? Is a customer something that exists outside of time? Is it something that exists at the time that the system was written or the ideas were created? When we move to the snapshot pattern, we have to make this explicit. So we have to make a distinction between the customer now, the live model of the real physical customer. So this customer object has intentionality. It's pointing to the customer in the real world. We will also maintain a whole bunch of snapshots of customers, showing what that same customer was like at a bunch of different points over time, up to the present moment. There are many variations on how to do this. The basic idea is we will make a distinction between the object representing the customer now, which is always the most up-to-date version, and we will extend that customer class with an extra method called getSnapshot. Again, if you're doing serious object-oriented programming, you probably have an interface called isSnapshotable or something, and customer will then implement that interface. It will be a contract promising that this class is able to give you snapshots of itself. We distinguish the live customer from, in this case, what is called a customer snapshot. This contains all the same information as the customer, but it extends it by adding a timestamp along with it. There's slightly different ways to set this up. You can have a dedicated customer snapshot class which copies all the data from the customer and adds a date, or you could take a clone of the basic customer itself and then wrap it in a new class which adds the date as part of the wrapper. Often you'll then want to take those snapshots and store them in a database or a hash table, some structure that enables you to quickly perform manipulations on them. And so again, it's useful to distinguish the customer snapshot from the timestamp so that you can use the timestamp as a key and the snapshot as the object being stored. There's a very interesting paper out there called Accountancy Design Patterns, which sounds like the most boring paper in the world, but it's actually full of this stuff. Accountancy is all about temporal histories of data. People who build accounting IT systems are much less boring than you think they are because they're forced to address some of these very ancient philosophical questions about the nature of time and the representation and conceptualization of time. They're forced to address them because they have to find systems that actually work and to code them up into databases and object-oriented programmings with time. The final claimed pattern I want to talk about is possibly the most controversial and is known as a monad. Or in particular, I'll be talking about one kind of monad called an option monad. Monads are usually considered to be a highly theoretical, abstract area of computer science. They are used in functional languages such as Haskell in particular. They are based on very difficult advanced mathematics known as category theory, and they tend to scare working programmers to the extent that working programmers don't usually bother to learn about them. What I'd like to present here is a different view of the monad as just another design pattern, as something that is no more difficult or interesting or scary than all the other design patterns. To do that, I'm not going to talk about monads in general very much. I'm going to talk about a special case of the monad known as the option monad. So you can maybe think of monads as a kind of meta design pattern, and something like the option monad is a particular design pattern that I'll discuss here. To motivate this, there is a very practical need for option monads. When I was working as a trader, one of the banes of our existence was missing data. Here's how to lose $10 million as a quantitative trader. There is a way of representing missing data known as NaNs. NaN stands for not a number, N-A-N. And so it's very common in financial data especially to have a long time series of numbers such as stock prices. And then when a piece of data is missing, instead of a number, we write NaN, N-A-N, in the data. So this happens a lot in finance. Most basically, the markets are closed at the weekend. So every Saturday and Sunday, tradable prices are NaNs. Then you have bank holidays. Bank holidays are called bank holidays because the banks are shut and the markets are shut. Exchanges can also close due to technical issues. They can be closed for political reasons. If there's crisis which causes the market to plummet, then the market may be closed for a period of time to stop panic trading. Or in other cases, people just make mistakes which causes data to be lost. Someone might have forgotten to turn on the data recorder for some set of stock prices on a particular day. So you will often find these NaNs mixed in with your data. They become a problem because most of financial data processing involves writing these little mathematical functions like the ones here. We've got an add function and an averaging function. And when you perform arithmetic on sets of data with NaNs, things can go very horribly wrong. So you might define basic rules of arithmetic for NaNs. For example, if you add a NaN to an integer, any integer, the result is NaN. 3 plus NaN equals NaN. Or if you multiply or divide by a NaN, you get NaN. Now this is okay if you're working with single numbers or a few numbers, but it's critical when you do aggregation operations, such as taking an average. You might have 10 million prices recorded over years, and they're all absolutely fine, except for one NaN sitting in the middle of them. So when you try and take the average of those 10 million numbers, you do this by adding them all together and dividing by the number of them. But one of those additions involves adding a NaN, and that makes the result of the entire average computation become NaN. So find this little tiny NaN explodes, it takes over your whole system. And in some cases, this can be horrific. You might run your detailed financial or machine learning model for a month and wait for the result to come out. It goes away, it calculates everything according to the equations. And because of that one NaN hiding in your data set of 10 million prices, the result of the whole thing just comes out as NaN, and you've wasted your month of computation time. So the traditional way of handling this, which is the non-monadic way, this is not what I would recommend doing now. It's what I did when I was a trader, and we made a lot of mistakes due to this, and we lost some money due to this. The traditional way is you're going to take your numerical library containing hundreds of little functions like these and some bigger functions with your fancy financial mathematics in it. And for each function, you are going to add some special logic to figure out how you should handle the special case of a nan being there. So for example, here's an add function, very simple function, add two numbers together. But we're going to add this bit of logic at the beginning that checks each argument, tests if it's a nan, and it does something special. In this case, it's just going to return a nan as the result of the addition. And otherwise, it's going to pass it to the usual calculation. When you get to an average function, like the one on the right, the nan is now handled in a different way. So now to take the average of a group of numbers, you have to step through them one at a time. You check each one if it's a nan or not. If it's a nan, you ignore it completely. If it's not a nan, then you increment an accumulator called total by that number. You increment the number of good values called n, and then at the end you compute the average by dividing that accumulated total by the number of good values. Now the problem with this is that your financial library consists of hundreds of these little functions and bigger functions, and you have to handle this obscure special case separately in every one. This is incredibly error prone. There's 100 different opportunities to mess something up, and in particular there are cases where you might think you've written the code and handled the nan, and the particular data you've been running it on all year has never actually encountered a nan, and then you put the system into live production use and one day it hits a nan, and then very bad things can happen. A better way to address the problem of missing data, which I only came across after doing that work, but I wish I'd known about at the time, is the option monad. Again, we're going to view this purely as a design pattern in this lecture. Here's a UML diagram for the monad option. The idea is we take a basic type, such as prices. Maybe prices are represented as fixed point numbers, whatever. Assume we have an existing class called price, and we create the option class, which is templated on an underlying type. So in this case, we're going to apply the option monad to price. We're going to create something called a price option whose type is an option of price. And the option monad has two subclasses which inherit from it. It can either be some of the type, such as some dollars, some price, in which case it has a numeric or other value, such as some 57.3 US dollars, or the option can be none, which means there's nothing there. Now, this is different from the nan concept, because in the nan concept, the nans exist as a price in themselves. They exist as a number that is not a number, as part of the same ontological category. What we've done here is separate out things which are prices from things which are not prices. Both of those things are subclasses of option or price option, but now if we have a value that is some US dollars, we are now guaranteed, we have a contract promising that some dollars is going to contain an actual numerical value. If we have a subclass none, we are then guaranteed that there is no value there. This is something which could have been a report of dollars, but isn't. So there's a difference between having $0 and having none. Okay, $0 is still a price. It still exists as a numeric value, whereas none means we don't know, the data is missing. So that's the first part of the solution. We create the option monad with those two subclasses, some dollars or none. The second part is that we now go and build our mathematical financial library in the old-fashioned way. This is without including any nan processing at all. Okay, this is the library we had before we went in there and started adding all this extra code for nan processing. So for example, our add function is now going to be this nice, beautiful, clean mathematical function which only worries about returning x plus y. Our average function can be very simple. We're just adding all the numbers and dividing by x's. And we do this by assuming that these are only ever going to run on some dollars rather than none. So this is nice because it means these functions can be written by mathematical experts who don't care about data wrangling, who don't care about missing data. They just want to get on with their financial modelling. They want to do difficult advanced maths, and they don't want that maths to be peppered with all this extra logic about handling special cases coming up from the nans. The clever bit is that we then pass those mathematical functions to the monads, not vice versa. Conventionally, if you want to do an operation on a bunch of prices, you will have a function that operates on prices, You will pass those prices to the function as arguments and you get a result coming back. Now we do this the opposite way around with the option monad. With the option monad, we give the function to the monad, not the monad to the function. In particular, this means that we can pass these very simple functions, which don't care about nans, we give them into the monad, and it becomes the monad's problem to figure out how to deal with the non-data. The monad is going to strip all that stuff out for us, and then it's going to call the function that we've asked for using only the good data, using only some prices. So remember, the function was written on the assumption that it will only ever get called with some, but the monad is providing the guarantees. We know that if we have some, then there is a price, and if there's none, then there is no price. So it now becomes the monad's problem to take an arbitrary function and to strip out all the missing data in order to call that function in a way that will make the function work. So here's an example. Here we've got a method called option.map function. It takes as its input a function from type to type, such as a function from price to price. So this function doesn't care about monads. It's written on the underlying data type, like price. And then it takes a set of arguments that we would like to be given to that function. And their type is a bunch of other options. And then the logic here, inside this single function in the option, is to do with stripping out all the bad data. In this case, we're selecting out all the data that is not none, and then we're passing that on to the function. Note that to do this, you need a language that is capable of passing functions around as arguments. That's standard in functional programming languages. It's becoming more common in other languages now that have been inspired by the functional languages, but it's not always possible to do this. So this is only scratching the surface of monads. The option monad is just one special case of the general monad pattern. To understand general monads is harder. You'll need concepts from functional programming. Just to give a flavor of it, for example, the list is another example of a monad. Option and list are two classic monads. And you'll see the monadic structure in list when you come across the map function. So if you create a list of integers, for example, you might have a function which adds 2 to a single integer, but you see the same monadic structure when you map that function across the list. You'll see the same structure where you give your add2 function to the list, and the list will then take care of applying that function to each of the elements within the list. So you can roughly see how this could get generalized then. The monad is really something that is taking a function as input, and it is handling these special cases of figuring out how to apply that function in different ways across an underlying data type which the monad is wrapping around. That concludes our study of samples of claimed modern design patterns. There are many more. If you're interested, go and look for books, go and look for blogs. Try and find the debates. There are many current ideas being proposed as modern design patterns, and some people like them and some people don't. So try and find a debate where you can see that process of canonization of a design pattern happening in real life. To finish, I would like to talk about anti-patterns. This is the dark side of design patterns. These are patterns which you should not be writing, but which are known to occur frequently. And as with patterns, if you learn to recognize anti-patterns and you learn their names, when you name something, you can control it, you can treat it, you can understand there are standard treatments to fix these patterns. It's a good way when you're working with other people's code, if they've made a design mistake, if you can point out they've made a classic standard anti-pattern, you might have a better chance of convincing them that they really have made a mistake. Let's begin with the classic anti-pattern of boilerplate code. This is where you cut and paste copies and edits of code in multiple locations in the software. The problem, of course, is that you will then find yourself updating one of these versions and not the others, and you get yourself into a big mess because you've lost track of which version everything is in, especially if you change two versions in different directions. Very difficult to recover from that. When we discuss anti-patterns, we'll often also discuss what are called code smells. Now, the anti-pattern is the underlying cause, the disease. The code smell is the symptom. It's something you notice that gives you a strong hint that an anti-pattern may be present. So the code smell for boilerplate code is, didn't I just fix this? You find yourself looking at a piece of code that you saw last week and you already fixed it, and now you're seeing it again in the unfixed situation. The way you treat this is by abstraction. The first rule of software engineering is anything can be solved with another layer of abstraction. So you're going to find some way to wrap up or encapsulate or otherwise abstract away what is being done in the boilerplate code. Even if the code has been copied and then edited into two different directions, you're going to wrap it up in something like a function with a parameter, and the parameter is going to give you the ability to say which version you actually want to use. You're going to put it all in a single place with no redundancy, and you're going to call it multiple times. Boilerplate comes from how we build battleships, by employing people to spend hours and days and months welding one boilerplate after another together. You should not be doing this as a grown-up software creator. If you ever find yourself doing a task repetitively, as in more than once, then you need to find a way to automate it and to remove redundancy. Typecasing. This is where we write code relying on typecasing instead of object-oriented overriding. So the code smell for this is you see a bunch of switch case statements. So for example here, we've got a function that is testing an input object called myPet, representing a pet. And it's testing, is this a cat or a dog or a cow? And it's saying, what should I do, purr or bark or moo? Now the problem with this is that every time we write a function, and this is a say hello function, but every function we write like this is going to have to do its own casing. That means if new cases ever get added, if new animals are added to the simulation, they will all need to be updated, and that's very error prone. People will forget to update these things, they'll find it hard. So the treatment is to give the animals more autonomy, give the animals a voice, and that means we move the methods to subclasses and we let the class system do the work instead of switches and cases. So in this case, we would move all this logic into a function called doStuff in each of the pet subclasses. So here we have a cat which is able to do stuff, and that will do purring. We have a dog that is able to do stuff, that will do barking. And this means that now when other members of our team add new animals to the system, as long as they implement those same methods, they can do it without having to let the authors of the calling functions know what they're doing. It's separating the differentiation of behavior from the caller. Anemic domain. This is a more controversial anti-pattern. So many people would claim this is not necessarily bad style. Hardcore object-oriented programming people and Java people especially will accuse this of being an anti-pattern. This is where we have many business logic objects functioning only as structs. They're only containing data, and the computation is getting done on them by additional objects. For example, we might have a class car, which just represents the data. It's got the age, the license plate, the speed, and so on. Class driver has data including location and frame rate. But then all the computation is getting done by another class. In this case, it's a driver location predictor. That's got methods with all the logic. It's taking those data objects as inputs, and it's doing the work of computation. The code smell for this is seeing verbs getting turned into nouns. So you see the driver location predictor. This should really be a verb. This should really be a command like predict the driver location, but you see it's got transformed here into a noun. And this object doesn't really represent anything in the physical world. It doesn't have intentionality like the car and the driver do. There's nothing out there in the world that is a driver location predictor. Object-oriented orthodoxy says that this logic should all be moved into methods inside the objects themselves. This should be a property or a method of the driver or the car rather than existing in itself. The treatment is you move the methods into the business logic object. So more recently, there's been something of a backlash against this style of object-oriented programming. There are people saying we should maybe go back to just using structs and defining functions on the structs, maybe wrapping them up in a module rather than inside the class. But by hardcore object-oriented people, this is considered an anti-pattern. Object cesspools. Before these were considered an anti-pattern, they were once considered a good thing and known as the more polite object pools. And this was a programming optimization usually done for memory access speed. And it was done especially in 1980s style code, when it was considered expensive in time to be constantly creating and destroying objects, because creation and destruction operators take time, especially for real-time systems. You might still find this being done. So a 1980s style workaround for this was to instantiate, say, 100 instances of class cat, and then to use those same 100 instances to represent a constantly changing set of different physical cats in the real world. So whenever a new physical cat comes into play, we will look at the object pool, the 100 cat objects that we created, and we'll say which one isn't currently being used, and we take over it, we populate all its data to represent the current physical cat, and then when that cat goes away, we'll put it back in the pool. And then the next cat that comes along, we'll pull the same computational object out. We will overwrite its data fields to represent the new cat. Problems occur here when you make a mistake in cleaning out the data and you leave all data in its place. And this will emerge as a code smell when you're trying to work with your new cat and you suddenly start seeing data in your new cat that is representing an older cat. The treatment for this, of course, is do proper object-oriented programming. The whole concept of object-oriented programming is supposed to be that one computational object represents one physical object. It has that intentionality. And you're misunderstanding the notion of what an object is if you're using the same computational object to represent multiple physical objects. So the treatment is to do it properly, use proper creation and destruction. Now you do still see this sometimes used in very real-time systems. For example, I once worked on a musical score following system. That's a system that listens to you play music and it understands where you are in the music and it provides accompaniment as you go along. And in that system we're creating thousands of hypothesis objects. A hypothesis is also known as a particle. It's a guess of where you might be in the music, but you're creating thousands of them and they all exist simultaneously, and it's all done in real time, and it would be expensive to create and destroy those. But if you use a decent modern language, the language designers should already know about this, and they should have already provided some kind of workaround for it. The God object. A God object is a single object containing masses of functionality. So this is often done by engineers trying to write code when they don't understand object-oriented programming. They will basically come and write a procedural program and they'll just put it all inside one great big class, and it's just a procedural program, and you're not getting any of the supposed benefits of object-oriented programming anymore. The code smells are that the single class code is very, very big. In particular, in my opinion, if code in a file is bigger than one screen, then it's too big. I tell this to my school children in Scratch programming, and I tell it to you guys as well. If your code is filling more than a screen, that's a strong smell that you should be splitting it up into smaller units. That will help you both as a programmer to see what's going on, but also as a designer to encourage more levels and hierarchy in your design. You'll also see this in a UML diagram when you have a single class taking up a whole A4 page with a vertical list of too many methods together. The solution, of course, is you split it into smaller pieces. Object orgy. This is many objects each probing each other's private parts. The original concept of object-oriented programming is that no one should ever have access to the private parts of anybody else. This is often claimed as a failure of language designers, which even allow that to happen. You should never be accessing member variables of another object directly. You should be going through at least getter and setter methods. The reason is that if you do this, you create problems when implementations change. The API of your class is supposed to specify all the things your class can do, but without reference to their implementation. And the API is supposed to remain constant even when you go off and completely change your implementation, for example, to make the code run faster or make it run in parallel. But if people are coming in and accessing your members directly, now your implementation has got all tangled up with your interface and you can no longer go off and change your implementation. And when you do change your implementation, bad things will happen and your users will complain that their code doesn't work anymore. The code smells for this, of course, are seeing things like this. My object.x equals 3. You should never be talking to a member variable directly. You should be going through a getter and setter. Even worse is the second example from Python. My object._x equals 3. So Python has no concept of private variables, but software engineers in Python use a convention, just a social convention, that if you name a variable with an underscore, that means you really shouldn't be accessing it from outside. To be honest, you shouldn't be accessing it anyway from outside, but the underscore is just a reminder of please really, really don't do this. So if you ever see anyone doing my object._x, that's very, very bad. They really shouldn't be doing that at all. The treatment, turn them all into getters and setters. When we talk about refactoring, there are ways to do this automatically. There are refactoring tools based on static analysis that will look for these cases and automatically replace them with getters and setters. That completes our tour of design patterns. There are hundreds of these things. We've only given a few examples. Before we go, I wanted to talk about criticism of the whole design pattern idea. Some people do not like design patterns at all. In fact, in extreme cases, the concept of design patterns has been considered as an anti-pattern in itself. Much of this criticism comes from criticism of the underlying languages, especially Java and C++. Design patterns are often seen as workarounds for failures in the language, and the critics say we should just fix the language and then the design pattern would no longer be needed. This is like everything in software engineering. People come up with new software engineering ideas, the language designers take them on, and then they're not considered software engineering anymore. They've become part of the language design. The design pattern concept, it's a very 1990s concept. It was very linked with a time of Java and object-oriented programming and UML and very extreme and excessive forms of object-oriented programming. We've seen in many of these patterns, they already seem a little excessive, where everything has to have an interface, everything has to have an instantiation. Sometimes you just want to get on with making code that works without getting into all that stuff. It can generate a lot of what is argued to be fluff when people come in and they write complete patterns rather than just implementing what is actually needed. That fluff may take the form of what is effectively boilerplate code. If you see people cutting and pasting design pattern code in multiple places, you're committing one of the sins of anti-patterns by adding redundancy and boilerplate. Some critics will argue that languages should be powerful enough to support the abstraction at a programmatic level. So for example, something like a bridge pattern should exist as a class in itself, or as a template, or as some other language-based structure, rather than as something that you have to do using the language. Patterns can promote over-engineering, or this whole way of thinking about design can promote over-engineering. There's a famous parable of the king's toaster, where the king asks an engineer and a computer scientist to build a toaster, and the engineer goes off and builds one using an Arduino and a few bits of metal. And the computer scientist goes off for the whole year and decides that actually you don't need a toaster, you need a generalized, abstract breakfast-making device. And the king has the computer scientist executed. Although then 3 years later, the king then decides that he would actually like some sausages as well as a toaster, and he wishes that he didn't execute the computer scientist after all. In some versions, told by computer scientists. Design patterns, if they're not used correctly, they may promote old-fashioned waterfall style designing. The idea that you have a design stage followed by an implementation stage. Some people will, I think, wrongly use design patterns as an excuse to go off and do that, to design things on whiteboards and with pens and pencils as a separate design stage. I don't think you should be doing that, but I don't think that's a design patterns criticism. I think you can just as well do your design stage using real code. I would always suggest that you create your UML sketches using real code. A UML diagram could be programmed as a PostScript file, either by hand or by using a graphical editor to create it, but it's just as easy to define that UML diagram in actual Python or whatever code. Just sketch out your classes, sketch out the functions, sketch out where the variables are, and then use an automated tool to just compile that into a UML diagram. And that's how you can do your design work as part of a modern, agile, iterative cycle. And finally, they're sometimes criticised just because of the stupid cutesy names. This all was done in the 1990s during a time of the Spice Girls and Oasis and the dot-com boom and object-oriented programming excesses. And part of that hype was creating these silly names like mementos and caretakers, which nowadays sound dated and not so useful. So with all that criticism, why should we continue to study design patterns today? Why am I teaching you this today? It's unusual for us to actually implement a design pattern directly today. I can't remember the last time I ever logged into my editor and said, I'll make a graphical object factory and pull out the Gang of Four book and copy out the boilerplate code for that particular pattern. Although one of the reasons we don't have to do that so much today is that much of our programming now sits on frameworks and middleware and languages which have themselves taken the design patterns to heart, and they've created their frameworks based around the design pattern so that you don't have to build it yourself. Arguably, this is addressing the criticism made earlier that these ideas should be abstracted away into actual code so that the programmer doesn't have to think about that. Say you're using this year's trendy web framework, you will almost certainly see a whole bunch of patterns that are baked into that. You don't need to recognize them as patterns in order to use it, but it may help you if you're faced with getting up to speed with a new framework, a new piece of middleware. If you recognize something and say, aha, that's a bridge, that's a factory, you instantly get an understanding of how that whole piece of software is put together. That means you don't have to spend as much time learning how to use it, and you can very quickly become an expert in these new systems from your knowledge of patterns. Or maybe just a few of you will actually be employed to work on those frameworks and middleware yourselves, and then you really do have to know the patterns in detail, because that's what you'll be building. The one place patterns do still show up is in GUI programming. We've talked all through this. We've seen there's a pattern of thought where you write your logic, your business logic, you have models of whatever it is, computer music or cars or financial entities, and then you somehow want to bolt on all this extra stuff that is going to display graphical representations of that stuff, and you really don't want to mess up the original code. Ideally, you don't even want to touch that code. You somehow want to have your graphics system dialing in or extending or interacting with the logic, but without actually having to change the logic. And you'll see many of the patterns that we've studied are very much positioned as GUI solutions. GUIs have this property where they don't really respect the original business logic hierarchy, the classes and the abstractions. So GUI often needs to dial in and see everything at all layers of the hierarchy and have access to it, but in a way that isn't going to mess up anything in the logic itself. But the main reason I suggest you study design patterns and read all of these excellent books and others and join the debate is to improve your own thought processes. We've talked all through this again about the difference between a pattern as a rigorously defined piece of UML and a class implementation versus its use as a more general idea and a way of doing things. And by studying big books of design patterns, you will just learn from the experience of thousands of programmers before you what works and what doesn't, how to think about programming in general, how to think about these particular ideas that you can combine together to help you in your own designs. Even if you don't follow a pattern exactly in this formal UML style, it will inspire and improve your thinking and your own sense of design as you transition from being just a programmer to becoming an architect. Not only your own internal thinking, but also your communication, your transmission of your thinking to other human beings. The patterns give us a shared vocabulary that everyone in our field is familiar with. So if you're trying to communicate your difficult idea for your new graphical interface, whatever, you often have difficulties getting that over to a human. But if you say, oh, it's a bridge pattern, or even if you say it's like a bridge pattern, but different in these ways. For example, when I explained the language server protocol to you, it's not a pure UML style bridge pattern, but I can tell you now that LSP is like a bridge pattern, and you know pretty much what I'm talking about. So the real reason to study this stuff is not just to cut and paste pieces of boilerplate code from the Gang of Four book. The real reason is to sharpen your own thinking, your own communications, and to make you a better designer and a better architect. Thank you.